Hello everyone, today let's look like a QP142 where we have 4 brand new light bulbs installed in a room at the same time. Each bulb's lifetime is an independent random variable exponentially distributed with a rate parameter 1. So what is the expected amount of time that will elapse until the last light bulb runs out? So basically I'm starting at some time, let's say time equals 0 right here, and this is when I install all 4 of my light bulbs, and they're all exponentially distributed with rate parameter 1, so they're all exponential, and maybe our first light bulb dies right here, maybe our second one dies right here, maybe our third one dies here, and then when our fourth one dies, that's going to be basically the expected value that we're trying to find. We're trying to find the expected time that it takes for this last one to die. So we could solve this the way that we've been doing, right? We're basically finding an order statistic here, right? The maximum of 4 different random variables that are identically distributed and independent. So this is an order statistics question, right? We're finding the maximum of 4 different identically distributed random variables. So we could solve this like we've been doing with the order statistics before, but basically you can realize that when we're doing Poisson processes, exponential distributions, things like that, there's usually a lot of nice properties that make it easier to solve than using all those integrals, right? So let's start with that. So let these 4 random variables be the lifetimes of my 4 lights. They're all exponentially distributed with rate parameter 1. So they're coming at a rate of 1 per time period. We're not told what the time period is, but we don't need to be. And all these processes start at the time t equals 0, right? They're all installed at the same time. So basically when we have 4 different Poisson processes happening at the same time, they're all happening at a constant rate and they're all independent. So when they all happen at the same time, it's basically one big exponential distribution with parameter 4, right? We sum up all the parameters. That's just, again, because with the Poisson process, if we have basically failures occurring at a rate of 1 per time period and we have 4 of them, then we expect 4 different failures to be occurring per time period when all of them are running at the same time. So therefore, since they all start at time t equals 0, the time until our first failure is going to be basically exponentially distributed with rate parameter 4. So this right here is the waiting time until any of these 4 fail. So for the expected time until the first failure, we derive the expected value of the exponential distribution in QP number 137. It's just going to be 1 divided by lambda, where lambda is our rate parameter, so in this case 1 on 4. So 1/4 is the average wait time until the first failure. So now what is the average wait time until the second failure? Well, once one of our light bulbs has burned out, we're not going to reinstall a new one, so we basically just lose one of these, right? The process ends. So right at the point of first failure, we have 3 light bulbs now remaining, and now what is their wait time until the next one of those fails? And we remember that the exponential distribution is memoryless, so no matter what point that we start waiting, right, if it's at the point of first failure, these are still going to be exponentially distributed with rate parameter 1 at that point. It doesn't matter where you start, right? So right at the point of first failure, the time until the next failure is now going to be basically the sum of these 3 exponentials, right? It's going to be now distributed as an exponential with the rate parameter 3. So this right here is going to be distributed as an expo 3, which again is going to have a mean, an average value of 1/3. So that is the expected wait time for us from the point of first failure to the point of second failure. And now we just need to calculate what is the waiting time until the point of third failure. Well, again, now one of my light bulbs has died and the exponential distribution is still memoryless. So at this point right here, we basically have a new exponential process starting with rate parameter 2, because now it's the sum of these 2, right? So from the point of second fail to the point of third fail, it's going to be exponentially distributed with rate parameter 2. And again, the average of that is going to be 1/2 by what we showed in QP 137. So that's the average wait time from the second fail to the third fail. And now finally, what is our wait time until the fourth failure? Let's do it in blue. Well, again, at this point right here, we'll have another failure. And again, the exponential distribution is memoryless. So now we have one exponential basically starting at this point right here. So an exponential with parameter 1. So the wait time between the third and fourth event is going to be distributed as an exponential with parameter 1. And what's the mean of that? Well, it's just going to be 1 divided by 1, or 1, right? Originally, we were trying to find the expected amount of time that will elapse until the last light bulb burns out. So from the time that we install them until the time of the final failure. So I'll call the time from 0 until our fourth failure W, and you can see that we're trying to find the expected value of W, but we can express W basically as the time until the first failure plus the time from the first failure until the second failure plus the time from the second failure until the third failure plus the time from the third failure until the fourth failure. And we just calculated the expected value of all these sums. So by linearity of expectation, right, we can just sum all these up. I'm going to sum up 1/4 plus 1/3 plus 1/2 plus basically 1, right? So that's just the harmonic series. So these are the first 4 harmonic numbers. If we get them over a common denominator, we're going to have to do, let's do 12. So I multiply this one by 3, I get 3 on 12. I multiply the next one by 4, I get 4 on 12. Multiply this one by 6, I get 6 on 12. And I multiply this one, well, it's just going to be 12 on 12, right? So that's going to give us 25 on 12, which will be our final answer. So the key fact that allows us to do this is the memorylessness of the exponential distribution. So right at the point of first failure, my next ones are still going to be exponentially distributed with the same rate parameter, right? It's going to be a new independent process. And at the time of this failure, it's going to be another new independent process, right? So that's what allows us to do this. If you wanted to do it the classic order statistics way that we've been doing, I'll do that down here. So I can use the same CDF trick that we've been using for the order statistics, right? The probability that the maximum of these 4 random variables, x1, x2, x3, and x4, the probability that that is less than or equal to some fixed value of t. In the case of 4 identically distributed and independent exponentials, there's going to be 1 minus e to the power of negative lambda t, where lambda is going to be 1 in this case, so 1 minus e to the power of negative t to the power of 4. Again, this is because if we fix some value of t, the probability that one of our exponentials comes before t is 1 minus the probability that our exponential comes after t, and the probability of that is the probability that no events occur before t, which we know is e to the power of negative lambda t when we plug in 0 to the Poisson distribution, right? That's how we derive the exponential. So the probability that one of our exponentials comes before t is just going to be 1 minus e to the power of negative t, and we have 4 of them, and they're all independent, so we just raise to the power of 4, and that's how we get this, right? And then to get the expected value of the maximum, all we have to do is to convert this into something that we can use with the tail sum. That's going to be the easiest way. So the probability that the maximum is greater than t, right? If this is the probability it's less than t, it's just going to be 1 minus this right here. So 1 minus e to the power of negative t to the power of 4. Then we integrate over all the possible values the maximum could take. So it could take 0 all the way up to infinity of basically this right here, 1 minus e to the power of negative t to the power of 4 dt. And then we can expand this a little binomial theorem action. We have the integral from 0 to infinity of 1 minus, then we expand this right here. We're going to basically have a 1. We're going to have a negative 4e to the power of negative t. We're going to have a 4 choose 2, so 6e to the power of negative 2t. We're going to have a 4 choose 3, so minus 4e to the power of negative 3t. And then we're going to have a 4 choose 0 plus e to the power of negative 4t, right? And all of that is with respect to t, and now we can just do a little cancellation. This is going to cancel right here. We're going to be left with the integral from 0 to infinity. When we apply this negative sign to all these terms, we're going to have 4e to the power of negative t. We're going to have negative 6e to the power of negative 2t. We're going to have plus 4e to the power of negative 3t, and we're going to have minus e to the power of negative 4t dt. For this integral right here, we're going to have negative 4e to the power of negative t evaluated from infinity to 0. That's just going to be 4. When we do this one right here, we're going to get 6 on 2 times e to the power of negative 2t evaluated from infinity to 0. So that's going to be negative 3. For this one, we're going to have negative 4/3 times e to the power of negative 3t evaluated from infinity to 0. That's just going to give us 4/3. And then for this one right here, we're going to have e to the power, actually 1/4 e to the power of negative 4t evaluated from infinity to 0 is going to give us negative 1/4. Then when you sum all these up, we're going to get 4 minus 3 plus 4/3 minus 1/4. So this term right here is going to be 1. Over a common denominator of 12, we're going to have 12 on 12 plus basically, what is this? 16 on 12 minus, what is this? That's going to be 3 on 12. So that's going to give us, again, 25 on 12. So that's the classic order statistics way. Again, it's going to be a lot easier just to do it this way, just by using the basic properties of the exponential distribution. You can see that it gives us a lot of nice features, right? So 25 on 12 is the final answer.